Hello, welcome to the first part of a series on Henry Bergson and his philosophy of mind, with emphasis on the holographic aspects of his theory, where these holographic aspects, we should say, have been not understood at all, precisely because he created his theory well before the advent of holography. So in part one, we'll be looking at the hard problem as coined by David Chalmers in 1995, which has to do with how either machines or human brains solve the problem of conscious perception and the qualities within experience, and Bergson's model of perception, which relates to the hard problem and is a solution thereof. And another way to put this is that we'll be looking at the problem of the origin of the image of the external world. Henry Bergson was a French philosopher, lived from 1858 to 1941. The height of his fame occurred probably around 1914, First World War, 1920. He died in 1941. After standing in a long line in occupied Paris, waiting to declare himself a Jew, died of pneumonia. His major works, and I stress major, there are other works, Time and Free Will, which held the essence of his insights, initial insight into the nature of time, and was his doctoral thesis. Matter and Memory, a book we'll be looking at in large part, and where he explored the question, is experience actually stored in the brain? And then 1907, a very famous work, Creative Evolution, exploring the actual mechanism and nature of evolution. And in 1922, Duration and Simultaneity, which was an analysis of special relativity, or the meaning of special relativity, and was in the context of an argument, shall we say, with Einstein and other physicists on the nature and meaning of relativity. And this eventually will become relevant to our discussion, as consciousness and time are intrinsically related. This is me, Steve Robbins. That's me standing happily by my chicken coop on my mini farm in Wisconsin. I have a PhD in educational psychology, minor in psychology, 1976, University of Minnesota. The focus was more on cognitive science, as we would term it today. I had a minor equivalent in computer science. And the thesis I did, PhD thesis, was on Bergson and his alternative model of mind. For, at the time, circa 1972, the whole notion of the brain as a computer swept into academics, into the University of Minnesota, into what ultimately became cognitive science. And Bergson presented, in fact, an alternative model to what largely became the theme of the day, unfortunately. I've got lots of academic articles on Bergson and consciousness. You can see these on my website, the website being in the description. Before my doctoral work, I spent some time in Vietnam, 1968, 1969. I was an infantry officer with the Marines, and managing to survive that, I returned back to graduate school and did my work above. Ultimately, I spent 33 years as an executive in the software industry because of all the computer stuff I had done, and now I retired, and therefore have time to make YouTubes. Now, I thought I'd better note here that I have done a few books on this subject that will help, since these YouTubes will not be going in that great a detail. So they're all on Amazon under my name, Stephen Earl Robbins. The primary one being Time and Memory, the primary on the scientific mysticism of consciousness. The next one is more oriented toward AI and the problem of the singularity and what Bergson has to say about that. And the next one is really a rewritten chapter of Time and Memory, the Myth of Special Relativity, which focuses entirely on the issue of relativity, Bergson's interpretation thereof, and it's important for this whole subject. So to set the stage for what we're really going to be attacking here, we'll be talking about the origin of the image of the external world. How we see the coffee cup on the table, external to us, out there in space. This is actually what has been termed the hard problem, so coined by David Chalmers in 1995, Chalmers being a philosopher. Article in the Journal of Consciousness Studies that became very famous. But the hard problem is not understood in the way that I've just stated above, as the origin of the image of the external world. Now bear with me, we'll be getting to how Chalmers coined the problem. But staying on this focus of the image of the external world, let's take someone else. In this case, John Searle, another philosopher, in his 2015 book, Seeing Things as They Are, A Theory of Perception, or in other words, a theory of seeing, or in other words, he's dealing precisely with this problem of the origin of the image of the external world. How is it we see the coffee cup out there on the table? A quote that's in the book is interesting. Quote, "Since the 17th century, I do not know of any great philosophers who have even accepted naive or direct realism," unquote. Now we'll be discussing direct realism and indirect realism, so bear with me a bit. But Searle's great philosophers, who were they? Kant, Leibniz, Hegel, Descartes, Berkeley, Spinoza, and Hume. Missing Bergson and the great psychologist of perception, the perception theorist, James J. Gibson. The problem, and why Searle has Bergson nowhere in his list, is that Bergson has never been understood by philosophy. He had a very powerful solution to Searle's problem, the origin of the image of the external world, also known as, I'm saying right now, the hard problem, how we see. But Bergson's solution is unique, nowhere in Searle's list of possible solutions. That is, nowhere in any of the list of solutions that Searle considers, including, of course, his own. Searle thinks he's defending what's termed direct realism. In direct realism, the coffee cup seen on the table is right where it says it is. It's external, in space, on the table, and our perception is direct. We're looking at the coffee cup right where it is, on the table, in space. The cup that we see is not just an image inside the brain. We're directly looking at the coffee cup. That's direct realism. But Searle's solution to how the image comes about is what's termed emergence. The image of the cup emerges somehow from the swirling neural processes inside the brain. This sounds perfectly reasonable except for one problem. Searle and no one else has any idea how neural firings or swirling neural processes can create an image. That's the problem. And likewise for Searle, this image having come out of the brain is still in the brain or in the head. So Searle is actually only what's termed an indirect realist. That is, the cup is real. The objects of the world that we're looking at are real. The chair is real. The table is real. But the images, the image of the cup, image of the table, chair, they're within the brain. So Searle actually spends much of his time trying to create a very sophisticated and involved method of correspondence between the image in the brain and the external world. And doesn't do too well. So having discussed the origin of the image of the external world a bit problem, let's take a look at the hard problem that Chalmers coined in 1995. It goes roughly or pretty much like this. Chalmers asked, given any neural or computer architecture, how does this architecture account for the qualia of the perceived world? So notice he's focusing on neural architecture or computer architecture. By architecture, we mean computer programs. We could mean the computer architecture itself. And the brain is a very similar problem. How the neurals, architecture, neural programs, whatever, are accounting for the qualia. Now, qualia, we need some examples. So a typical list would be the blue of the coffee cup, or the clinking of the spoon as we stir the coffee, or the aroma, the coffee aroma of the coffee, or the silveriness of the spoon. In a computer, as Chalmers was pointing out, all you have is changing bit patterns, ones and zeros, or a bit or a byte of these, 1100, 1110. In other words, you have patterns that change, but they're very homogeneous. How do you get blues, clinkings, aromas, silveriness out of changing bit patterns, other than by simply attributing to these changing bit patterns the blues, the clinkings, the aromas, etc., which is no explanation at all. It's simply begging the question. But likewise in the brain, just to pick a level of description, say the neurochemical, you only have neurochemical flows. Yet somehow out of these, you're supposed to get the blues, the clinkings, the aromas, etc. So this is the hard problem. How do you account for the qualia of the perceived world? The difficulty is that the hard problem is an extremely misleading formulation of the problem. Philosophy has been focused entirely on the on the origin of qualia. We're always trying to discover, from a philosophical point of view, how we get qualia, the bluenesses, out of the neural architecture, or how we get aromas, or how we get clinkings, etc. An explanation of the origin of the image of the external world, however, that's not important. In fact, it's not even seen as a problem. What's wrong with that? Well, the first problem with this formulation of the hard problem is that form, particularly in its dynamic aspect, is qualia. A good example is in Valerie Hardcastle's qualia examples in a book, Locating Consciousness, in 1995. Here's her examples. The conductor waving her hands, the musicians concentrating, the patrons shifting in their seats, the curtains gently and ever so slightly waving. So she's obviously in a symphony setting, observing all of these things happening, all creating a quality of the experience, and each being a quality within this larger experience. the conductor waving her hands, the concentration of the musicians. Obviously, the whole quality of the experience could be changed if the patrons started rioting, the musicians throwing their violins against the wall, etc., and the curtains ripping off and falling down. Quite different quality of the whole experience. But the key point here is that what we're talking about is dynamic changing forms over time in this image of the symphony. Now, forms fully populate the image of the external world. The cup, the table, the stirring spoon, the swirling coffee surface. So it's not just bluenesses, it's just not, or aromas or blueness. It's everything in the image, the forms, the blue of the cup and the form, the aroma, it's all part, everything in the image is qualia. The forms are qualia. The entirety of the image is qualia. The real hard problem is this. It's the origin of the image of the external world. It's accounting for the image as a whole. Qualia, as stated, is simply a part of this general problem. Now, there's a standard model of perception that enhances and exacerbates this particular problem. In this model, we have the external world outside the brain. We have the coffee cup, we have the radio playing music, and the light rays from the coffee cup strike the receptors, sound waves from the radio strike the receptors in the ears, and this information from the receptors is transduced and encoded, creating an internal world. Now, we already know the internal world. We have no idea what this internal world looks like. If it's simply encoded in the neural structure, it's a neural encoding. So we have external world information being encoded in the brain. But there's a problem, an inherent problem with the code. I call this the coding problem. It could equally be called the problem of representation. That's the more likely term in academics. But the coding problem is much more focused and easily to describe as in terms of the actual difficulty. So we take 3 dots, 1, 2, 3 dots there, and we say, well, those 3 dots could stand for an S in Morse code, the number 3, the 3 blind mice, or Da Vinci's nose. In other words, how do you know what domain a code maps to? It could map, those 3 dots could map to mice, to nursery rhymes, a Morse code letter set, numbers, Da Vinci's face. But the neural code looks nothing like the external world. So the question becomes, how can you unfold a code as the image of the external world without already knowing what the world looks like? Which is to say, you must already understand the domain, in fact, grasp the domain of this code, which is the external world. But the code is supposed to be the very method by which you grasp and understand what the external world looks like. So we have a deep logical problem with the brain as a coding mechanism. Extremely difficult. Now, there have been many approaches to this coding of the external world. For example, we just discussed the neural code. Or you can talk about the quantum level and say, oh, everything's in a quantum code, but nevertheless, the quantum code doesn't look like the world either. The quantum code does not look like the coffee cup there. You could pick a middle level, such as a molecular code. You have the same problem. You could go with Carl Pribram and say the brain is a hologram itself. So now you have a holographic code, but nevertheless, You still have a code that looks nothing like the external world, even less like the external world, and somehow have to decode that. No matter what level of description, you still have a code. So the hard problem is extremely tied to the coding problem. If you're going to solve the hard problem, you have to solve the coding problem. That is, the hard problem being the origin of the external image. What you have there in the brain is nothing that looks like that coffee cup out there in the external world. Now, there have been many attempts to solve the hard problem, which is to explain the origin of the image of the external world, though often this isn't even recognized. One example is the theory of higher order thoughts. For example, a thought of the coffee cup is somehow imposed over the neural processes of the brain and helps to unfold that code as the image of the coffee cup. I'm putting this nicely. Obviously, to have a thought of the coffee cup, you already have solved the problem because you know what the coffee cup looks like. So the problem is an inherent bootstrap problem right off the bat that invalidates it, or the solution, the higher order thought solution, as the bootstrap problem. A neural program, like a computer program that somehow runs against all this coding and creates an image, but that's exactly the same problem. How does the neural program know how to create an image of the external world? Synchronous oscillations have been proposed where the various parts of the brain get in sync in oscillations, but this does not actually solve any problem for how the image is created out of the code. It just syncs up various sites of the brain. You've got an inactive approach which emphasizes action as part of perceiving the external world, but robots can act. Action in and of itself does not explain how a code is unfolded as the external world, as the coffee cup. Externalism is a philosophical position that sees the brain as embedded in the external world, which is nice, but it doesn't speak directly at all to how, once you've got the information encoded, that external world is now perceived as the world of coffee cups and spoons and tables. There's an integrated magnetic field has been proposed, that where the brain is generating magnetic fields, and somehow a magnetic field is given the property of being able to take this code and still unpack it, interpret it as the image of the external world. Of course, there's no theory whatsoever as to how integrating magnetic field could do this. And finally, we've just seen emergence as what is in reality a standard effort at this also, where we simply take on faith that somehow these properties, the image that is, the coffee cup, emerges from the swirling process of the brain, which is in essence a surreptitious and rather lousy solution to the coding problem. So none of these solve the problem of the image of the external world. So far, we've said this: the image of the external world is filled with forms, and the forms are qualia themselves. The hard problem is the origin, or the problem of the origin of the image of the external world. A solution to the hard problem must explain the origin of the image. And a solution to the hard problem must solve the coding problem, which I think I've noted also is known as the problem of representation in academic circles. But as you can see, given the efforts in the hard problem solution, the coding problem is hardly understood at all. So now to Bergson and this problem of the image of the external world. The creation of an image is an optical problem, firstly. It's a problem of physics. In this case, it is also a problem in physics' model of time. And Bergson had a solution that covers both. The key is in a passage in Matter and Memory in 1896. Bergson noted that there is no photograph of the external world to be found in the brain. We don't see anything in the brain, in the neural processes that look like the coffee cup and spoon. We see neurochemical flows or whatever level of description, whether it's jiggling atoms or randomly moving quantum fields, whatever. We have no image of the coffee cup there. Bergson went on. And this is the key passage in Matter and Memory. He said, "But is it not obvious that the photograph, if photograph there be, is already taken, already developed in the very heart of things and at all points in space? No metaphysics, no physics can escape this conclusion. Build up the universe with atoms. Each of them is subject to the action, variable in quantity and quality, according to the distance, exerted on it by all material atoms. Bring in Faraday's centers of force. The lines of force emitted in every direction from every center bring to bear upon each the influence of the whole material world." Now, this passage was entirely obscure to Bergson's contemporaries, and it was so to me for a long time. Truthfully, I had to read Matter and Memory inside and out, backwards and forwards and backwards, many a time before, and had certain experiences that were serendipitous that helped me see what was going on. The problem here is that 50 years before Dennis Gabor's discovery in 1947, Bergson had anticipated the essence of holography. So let's take a look at holography for a second, or image reconstruction, or better, wavefront reconstruction, more precisely. Here we have a typical setup for making a hologram. We have a laser, we have a half mirror, we have a hologram plate or a photographic emulsion plate, and we have objects of which we're going to make a holographic scene, in this case, a pyramid and ball. Now, the first thing that happens is we send out a wave. It's called the reference wave. The wave passes through the half mirror and covers the holographic plate. I've noted that as having a frequency, F1. But half of it bounces off the half mirror, part of it bounces off the half mirror, and reflects off the scene. And this, I'm just showing the ball, but the pyramid as well. And then, of course, that wave reflects back onto the hologram plate. It's now known as the object wave. That piece that's reflecting from the object scene or the object is called the object wave, and it covers the hologram plate as well. So what you have in a hologram is the interference of these two waves. An interference pattern is recorded on the hologram plate. The interference of the reference wave and the object wave. That interference pattern looks nothing again like the pyramid and ball. It's just a interference pattern, and would be indecipherable as a pyramid and ball. So how to get the pyramid and ball back out? Oh, and I forgot to say. So what you have in reality is a complex code on that plate for the pyramid and the ball. So to reconstruct the pyramid and ball, or to decode the pyramid and ball from the information recorded in the hologram, what we do is send a reconstructive wave back through the hologram. The reconstructive wave has to have the same frequency as the reference wave. So in this case, frequency 1. The reconstructive wave is deviated in 3 directions. The direction going downward forms what's termed the real image. And if one were to place a piece of paper at the point where they strike, one would actually see spots of light there, or a spot of light there. One deviation is straight through, the undeviated waves, and then the set of rising waves toward the viewer eye are the waves that specify the source of the original wavefront. That rising wave specifies the source of the wave as the pyramid and ball, and that's what the viewer sees in space, in depth, in 3 dimensions, the original scene, pyramid and ball. Now, I can record another interference pattern on the same hologram plate. I could use frequency 2 as my reference wave. I could use a chalice as the scene and record the interference pattern of the reference wave and object wave from the chalice. Now, if I modulate to frequency 2, well, let's see. I reconstruct the chalice, or maybe that's just a wine glass. So by modulating the reconstructive wave from frequency 1 to frequency 2, I now pull out the image of the chalice. I could record yet another interference pattern on the plate using frequency 3 and using the cup as the object for the scene. Then modulate the wave again and modulate the reconstructive wave to frequency 3 and the image of the cup is specified. Now the rising waves specify, toward the viewer specify the cup as the source of the original waves. Notice what I'm doing here is decoding images, information from the hologram by modulating the reconstructive wave. Again, modulating back to frequency 1, I reconstruct the wavefront from the original pyramid and ball again. So I can modulate these waves back and forth, frequency 1, frequency 2, frequency 3, etc., and reconstruct information on the hologram plate. This brings us to certain properties of holograms we have to discuss briefly. For one, each point of the object, say from our pyramid, gives rise to a little spherical wave. That is, you can visualize the pyramid, each point of the pyramid is giving rise to a little spherical wave, and the little spherical wave covers the entire plate. So the wave from each point in the pyramid covers the entire plate. Thus, the information for each point on the object, in this case the pyramid, covers the entire hologram. There's a converse, therefore. At each point of the hologram, there is the information for the entire object. Or put another way, at any point of the hologram is the information for the whole object. So, to verify this, one can take a tiny chunk of our original hologram plate, pictured there, beam the reconstructive wave, in this case frequency 1, through it, and we'll still see the whole object, the whole ball and pyramid, in somewhat degraded form in quality, but nevertheless the entire object is there. So even a tiny portion of the hologram can be used to reconstruct the entire object or scene. Now, this is the interesting point. The universal field, the field of matter, the universe, can be considered a vast interference pattern. Viewed as a set of waves, each point in the field is reflecting or carrying information for every other point, for the whole. David Bohm, in 1980, a physicist, already went there in his book, Wholeness and the Implicate Order. That is, he visualized the universe as a holographic field, a vast interference pattern. But Bergson had already gone there in 1896. He had envisioned the universe as a holographic field. This was his photograph, already taken, already developed in the very heart of things and at all points in space. Now, Carl Pribram in 1971 had viewed the brain, or the brain itself, as being a hologram. That is, he thought neural firing patterns created a vast interference pattern within the brain. Pribram's theory was not particularly that well received or followed up on, but Bergson had the correct model. Bergson's solution was this, that the brain is or is creating a modulated reconstructive wave. That is, the brain is the modulated reconstructive wave. This brain-created wave is passing through the external holographic field. And the wave is then specific to or specifying a subset of the vast information in the field. That it is specific to a source within the field. Like the wave is passing through the hologram is specific to a source of a wavefront like the pyramid and ball or the cup. So the brain is specific to a subset of the vast information in the field, or in other words, to a source within the field. By this process, now an image. The coffee cup, the table, the stirring spoon. Now we need to look at this from another passage of Bergson to see another aspect of this holographic specification, or brain as a specifying wave of the external world. The passage goes like this. Only if we consider every other given place in the universe, we can regard the action of all matter as passing through it without resistance and without loss, and the photograph of the whole as translucent. Here there is wanting behind the plate the black screen in which the image could be shown. Our zones of indetermination, which I will note are organisms, sources of free action, play in some sort the part of that screen. They add nothing to what is there. They affect merely this, that the real action passes through, the virtual action remains. So let's unpack that statement. The virtual action remains. In Bergson's terms, the universe is a vast field of real actions rippling everywhere. For real actions, for concreteness, one can read waves. So these real actions or waves create a vast interference pattern. Any given object acts on all other objects in the field. In fact, that object is obliged to transmit the whole of what it receives, to oppose every action with an equal and contrary reaction, to be, in short, merely the road by which pass in every direction the modifications, or what can be termed real actions, propagated throughout the immensity of the entire universe. So the subset of these actions, or information, that the brain-created reconstructive wave picks out is related to the body's own action capabilities. Its action relatability, that is the information selection principle from the holofield. Obviously, this field of interference patterns, vast field, is full of information, but what's relevant to the body is that to which it can act. Thus, Bergson stated, we're perceiving, our perception is virtual action. Perception is virtual action. We're seeing how we can act. That is, the information being specified as a subset of this universal field is a subset related to action. So the coffee cup is simultaneously a specification of something that the body can act upon. Now, this is a radical implication we will discuss later. So in this model, the brain is not generating, it is not creating an image. The brain is not projecting an image to somewhere out there, external to us. The image is not emerging from neural processes. Rather, the image is a specification of a subset of the field, of a source within the external holographic field. Or, put another way, the brain-supported wave is specific to specifying a source in the field. The coffee cup, for example, is within the external field, right where it says it is. It is not within the brain. So from this perspective, the brain is not an encoder. It is the decoder of the holofield. It is decoding a subset from the vast information available within the holographic field. Note 2, we are not explaining how perception arises. That's not the problem. Rather, we are explaining how perception is limited. The holographic universal field is perception. That vast interference pattern where each object is reacting to every other object, each point in the field is reacting, influenced by and influencing every other point, is perception. We'll explore this more later. The brain as a reconstructive wave is specifying a subset of this universal perception, and the subset is now an image of a source within the field. As we shall see, an image at its particular scale of time, and of course from a particular perspective, that is from the body as the source of the perspective. This is the ultimate in externalism, never mentioned by the externalist, another philosophical position I won't go into, but externalism in the sense that everything is really out there in the external field. It's the ultimate in direct realism, never mentioned by direct realists such as Searle. That is, Bergson just plain isn't understood or seen as an externalist or a direct realist. But with a vast difference. We have an actual physical mechanism for the origin of the image of the external world. That is, we have the brain conceived as a reconstructive wave, a very real concrete wave passing through the very real concrete holographic field, and specific then to an image, a source within the field. Now let's pause for a second and think about what this is in relation to the computer model, or the computational model, which the computer model really is. The brain is a very concrete wave. A reconstructive wave is very counter to the computer or computational model of mind. There's recent findings in neuroscience that indicate that the neural processes, when taken in larger group scale, are indeed creating electromagnetic fields. They're just not decoding anything. You can see that in the book, The Relativistic Brain, 2015 book. But the point here is, in other words, the brain is indeed a very concrete device. It's creating magnetic fields under one view. It's as a very concrete device, as concrete as an alternating current motor generating an electric field of force. So in the computational model, however, abstract computations are given all the work. Any device is sufficient. An abacus, a register machine using beans and shoe boxes, a Turing machine with a read head and infinite tape. All of these are utterly different dynamics. It doesn't matter what the actual physical dynamics of the machine is, whether it be abacus, beads, beans, shoeboxes, tapes, etc. As long as the abstract computations can be carried out, as long as I can do A plus B equals C, the concrete dynamics are irrelevant in the computational model. The concrete dynamics are irrelevant, only the abstract computations carry the work. The difficulty is abstract computations cannot account for consciousness or conscious perception. You need a real, concrete, specific dynamics with specific materials. You don't make an alternating current motor from rubber bands, toothpicks, and shoeboxes, nor do you make a modulated reconstructive wave. So this model is very dependent on a very concrete dynamics by what would be quite an incredible engineering feat to reconstruct. It's a form, in reality, here of broad computation. This is a form of computation fully acknowledged by Turing in his O machines or oracle machines. And we'll simply deal with this down the road. So where are we going down the road, long term? Much is yet to be covered to explicate the model. 1, how does memory work? For experience is not occurring solely within the brain in this model. Therefore, it cannot be stored there. Remember, the coffee cup is being seen precisely where it is, in the external field. The experience is the external field, so you cannot store this in the brain. What is cognition or thought? Why does it require consciousness? Interestingly enough, no current model of cognition incorporates or even needs consciousness. We're going to find out why you do. The relativistic notion of time. Does Bergson square with it? No, does not square with it, and we'll find out why. But we'll also find out what's wrong with the relativistic notion of time. What is free will? Voluntary action. How do we act? That is, even lift a finger. Major problem and interesting in Bergson's framework. And framework it is. This is a new framework for mind. I'm not going to be giving any details on the neuroscience that might underlie it. As you can probably see, the neuroscience has to attack what's going on from a theory, from a theoretical framework. And if you're in the wrong framework entirely, that is the computational model, neuroscience is not going to really get you anywhere. So where are we going next? Well, firstly, we're going to the great perception theorist who I said Searle left out, James J. Gibson, and aspects of his theory of perception. For Gibson, there's plenty of mathematical information in the external environment that modulates the brain in its role as a reconstructive wave. I've got a little picture here of an optical flow field where you have velocity vectors flowing by that are specified by a little equation. Basically, they're proportional to the distance squared. Rather ubiquitous fields as we drive down roads, for example, but very precisely mathematically specified. Secondly, we have to note this. We're always viewing the past. So the perceived wing beats of the buzzing fly flying by at 200 cycles per second are long gone by the time we perceive them. So how is this possible? How can we perceive the past? This is a subject that moves us deeply into the problem of time. And we have to go there to truly understand Bergson's model and what I just said. Thirdly, we must remove the homunculus, the lurking concept of a little man, that is an homunculus, that sits in the brain and views a projected image. In reality, there is no projected image. There's a specification of the source within the field. But this again moves us deeply into the problem of time. We must come to understand this statement of Bergson's. Questions relating to subject and object, to their distinction and their union, must be put in terms of time rather than of space. Now this is virtually a Zen koan-like statement, a sound of one hand clapping. It took me quite some time to understand what it meant, though it caught my attention instantly as I started reading Bergson. So I'll say, if you think you understand what I presented thus far in terms of the holographic model of Bergson, but don't understand this statement, which is required to make it all work, well, there's a slight illusion going on, which I cannot blame you for because I haven't explained it yet. So that's to come. We will look at Gibson in part 2, both how he supports Bergson and how Gibson's theory must be understood in the context of Bergson. Until then, signing off.